Let us take a continuous beam problem, simple beam problem. Let us take this example. The beam fixed at one end, subjected to a uniformly distributed load of 60 kilonewton per meter, the span being 4 meters. I will take here to be constant, A, B, C. So let us follow those 4 steps in analyzing this particular beam. So, first step. So find the static indeterminacy, that is 2m plus or minus 2j. Here m is equal to number of members, that is 1 member, 2 members, that is 2 members, 2 into 2 plus r is number of unknown support reactions. So here we assume axially rigid. So here you have, instead of 3 reactions, only 2. Here 1, here another 1. So totally R will be 4 minus 2 into number of joints. So 3 joints are there, A, B, C, 3. So this is 8 minus 6. To degree of static indeterminacy is 2. And degree of external static indeterminacy is R minus 2, that is R is 4 minus 2, 2. So externally indeterminate to the degree to this particular structure. Total indeterminacy is 2, so internal indeterminacy is 0. That is total indeterminacy minus external indeterminacy. So this particular structure is internally determinate, externally indeterminate to the degree 2. So in order to make it determinate, I have to introduce at least 2 external releases, 2 external reactions I have to remove. Hence to make structure determinate, we have to introduce 2 releases in order to make it determinate. In order to make, that already I have told you, hence to make structure determinate, we have to introduce 2 releases. That is why we have to determine first its degree of static indeterminacy. To know what are the, how many forces we have to remove in order to make the structure determinate. So since the degree of indeterminacy is 2 and the 2 externally indeterminate to the degree 2 of the external reactions we can remove it. So in general, all beams at single story rigid frames, they are all only externally indeterminate. It's a rule you can always remember, only external reactions you can remove in order to make it determinate. And also, of course, some imposed boundary conditions also you can do it, because here the formula is minus imposed condition, that's also there. We can introduce some internal hinges also we can introduce in order to make it determinate. So here there are various possible ways of making the structure and introducing the 2 releases. One is we can remove these 2 support reactions at B and C. If I remove it, it becomes cantilever. So it becomes a stable structure. So while introducing the releases, the structure should be stable. That you have to make sure. So by removing this, it becomes a cantilever. So it is stable structure. That is one possibility. Second possibility is you can remove the moment here. So make it hinged end, and you can remove this support, mid support here. So 2 reactions you can remove. So thereby you can remove 2 releases and make the structure determinate. Or you can make this hinge and introduce one internal hinge here. and B also internal edge. So that's also possible. So like this, there are various ways of making the structure determinate. Hence, there cannot be, we cannot just formulate a strict, definite step to be followed for this flexibility method of analysis as we do for stiffness method. So it is not possible to have a general procedure laid down so that it can be worked on computer. It becomes very difficult to write programs because there are various possible ways of making the structure determinate. That's one thing you have to remember. That's why most of the computer program, they use a stiffness method rather than this flexibility method. So let us choose here, let us choose the moment and support reaction here as the redundant. Let us choose the moment at MA, at A, and reaction, vertical reaction at B, that is RB, as redundant or released force. That's what first step. Find the degree of static indeterminacy, identify suitable coordinate, that is whatever you have released in order to make it determinate. Of course, that comes in second step that I have told there itself. And I have identified the coordinate. So the basic determinate structure now, since I have removed the moment at A, it becomes H. I have removed the reaction here at B, so that also comes like this, just free. Here it is roller only. This is C. This is how the structure looks like. This is called determinate structure of the given structure. So the coordinates I will identify like this. Since I have removed the moment, that moment I will take it as clockwise direction. That's the coordinate. That's the positive direction of the moment. Removed here is like this. This is the coordinate 1. The next, I have removed the reaction here at B. I will take that coordinate acting down. So this is RB. Reaction B acting like this. So you can choose in any direction. It is at your hand. So there is no definite rule. So I will choose acting down as positive because all nodes are also down. I will take, since it is acting up, I have to get a negative sign at the end. That I will reverse. To start with, I will take in the positive direction only. That you have to be very careful. I am not taking upward direction. There is some reason behind it. So just take it down only. So I have taken two coordinates. One is RB. Another is MA force. These two forces I have removed and make the structure determinate. Next second step, we have to evaluate the displacement along those releases. That means since I have removed these restraints, these are all the restraints which were there earlier. This rotation was not occurring earlier because it was fixed. Now I have removed that restriction. I made it here. There will be rotation occurring here. Similarly, here it was not allowed to move up or down because there was a roller support. Now I have removed that. Now it is going to move in the vertical direction, either up or down, whatever it is, depending upon the load. So these are called the inconsistency in the deformations. One is rotation, other translation here. Those two I have to evaluate for given loading conditions. That is your second step. And evaluate the displacement along these releases due to the loads. Due to given loads, you have to just find out those displacements. That is here rotation, that is theta A, here translation, that is YB, deflection at B. Both. This you can evaluate either using your dummy load method or using by remembering by the standard expression. So, second step to find displacements. Along coordinates 1 and 2. The coordinates chosen 1 and 2, we have to determine displacement. So you take the load in the basic determinate structure. Mind it, now the structure has become determinate. So using standard formula or dummy load method, you can evaluate these displacements. So the given load is UDL of 60 kilonewton per meter. So it will just displace in this fashion. I have to evaluate this theta A and this YB. So this D, the displacement on account of the load, I will indicate it by the matrix D. This D is nothing but your theta A and YB. So this theta A, I will use the standard formula that I will give you. You can also remember. So if there is a beam here, simply supported beam subjected to constant UDL like this, then it will deflect in this fashion. So the slopes at the end, here this is W if you call it, span is L, and the slope here developed at the ends is given by W L cube by 24 EI, where EI is the flexural rigidity of the member and L is the length of the member. This is also WL cube by 24 EI. Of course, this is negative, this is positive. While taking the sign coordinate, I will take in this fashion itself. Here it is clockwise. So here also I have taken clockwise only. To make sure whatever the coordinate direction you have chosen, that will be consistent with this particular displacement. And here the central displacement is given by 5 by 384 W L4 by EI. This formula you can remember for UDL case. Using this right away, I will work out. Otherwise, you have to adopt dummy load method for calculation of that displacement. So now I will use that standard formula theta A. As per this formula, this theta A is given by WL cube by 24 EI. W is 60 kilonewton per meter. That's 60 into L cube. L is now, mind it, it is 8 meters, not 4 meters. Because I have removed that B, it becomes totally 8 meters. That is 60 into 8 cube divided by 24. EI is EI itself. Just I have taken EI constant here. Suppose if this is 2 EI, then you have to adopt your dummy load method only. There is no other go. I have made the thing simple. I hope problems also will come like that. So otherwise you have to waste more time. So there is no point in taking up that problem for working. That you just remember in mind, and that if you don't have any choice, well, you have to just do that only. But it will take time. That remember that particular thing. If it is this is 2 EI and that is EI, then well, you have to go for strain energy method only. So here I have made the things simpler so that it is. So this particular thing
1280
1280
divided by EI.
By EI. So this is that theta A. On same lines, this YB, I have one formula. It is 5 by 384 WL4 by EI. So that is 5 by 384 W is 60 into L to the power of 4, that is 8 to the power of 4 divided by EI. This, if you simplify, you will get
3200. 3200.
3200 divided by EI. So these are the values. Therefore, my D, that is displacement matrix along those releases or redundance on account of the external load is given by 1 over EI. I will take it outside. It will be 1280 and 3200. So this is your second important step. So if, as I told you, if the EI values they are different, then this itself will take much time to you, that you have to decide whether to attempt the problem or not. That I am giving a clue. So you have to decide at that second point, otherwise don't waste unnecessary time. If it is standard case, you can just proceed it. Then next, third step, find the flexibility matrix. So this is another important step, so which you have to follow. So that is third step, that is flexibility matrix. Flexibility matrix, yes. So now there are two coordinates since, or two redundancies, since there are two coordinates or two redundant sides of flexibility matrix is 2 by 2. This is same as your stiffness method of analysis, 2 by 2, depending upon degree of static indeterminacy. There, depending upon kinematic indeterminacy, you are fixing the sign. Therefore, the matrix 2 by 2 matrix in general, I can represent it as F11, F12, F21, F22. It consists of 2 rows and 2 columns. It's a 2 by 2 matrix. Now I have to determine all these coefficients or flexibility coefficients or flexibility influence coefficients. This already I have defined F11, Fij. I defined as the force developed on displacement developed on account of unit force applied along those coordinates. That means here now I have to apply unit force along the coordinates 1 and coordinate 2 chosen and find out the displacement or forces, the displacements on account of that. So first I will take the first coordinate, of course in the basic determinate structure only. So this is A, C and B is here. Now first I have to apply a unit force. P is equal to 1 along the coordinate 1. When I apply this unit force, it will deflect in this fashion. So I have to find out the displacements on account of this unit force. This displacement here on account of this force is the theta 1. Here again displacement. This is on account of the moment. This is also standard case. You can remember, if you can remember, that is better. That also I will give you here. Suppose you have a simple beam subjected to a moment m at one end. If L is the length of the beam, here is the flexural rigidity, then this beam has to deflect like this. When this rotation is given here like this, it has to displace like this, and this displacement rotation, here it is given by, you can remember, ml by 3ei, and rotation at the forward end, it becomes ml by 6ei. This you can remember, and this particular displacement, of course I will give it. This displacement at any length x, at any point x, this delta is given by, that is the formula, m into x divided by 6ei L into x square minus 3lx plus 2l square. This formula you can remember and you can work out what all the displacements occur. So this formula you can remember for this case. So using that formula straight away, I will determine the flexibility coefficients. This F11 is given by, that is this, F11 is this. This is my F11, that is the displacement along coordinate 1 when unit force is applied along 1. So this will be F21, that is the displacement along the coordinate 2 when force is given along 1. So both this F11, F21, that is the column 1 of the flexibility matrix, I can easily generate the moment I know that particular standard formula. F11 is given by this ml by 3I. M here it is unit moment force applied. 1 into L is 8 meters divided by 3 into EI, that is 2.67 by EI. That is my first coefficient F11. Then F21, it is from this formula you can determine that's a displacement. Displacement at any distance x from left hand I have given. That formula you have to remember at least for the standard cases so that you can work the problem with very easiness. Very easily you can work the problems rather than dependent working using resorting to unit load method. So this F21 is m is 1, x is this distance. So that is at 4 meters I need this 1 into 4 divided by 6. EI is 6 EI L. L is 8 meters. EI is EI itself into x square, that is 4 square, 16 minus 3lx, that is 3 into 4, 12, 12 into L is 8, 96. Then 2L square, L square is x square, x square is 64 into 2, that is 128. So you can simplify this, 128 minus 96, it is 32, 32 plus 16, 48. This you will get 48, so this 8, 6 get cancelled, I think you will get 4 by EI. That's simple calculation. You need not waste much time, provided if you remember that formula. Then, next case, this first column I have generated, second column I have to generate, that is I have to give unit force along the coordinate 2. So you take the determinant structure, that is this beam itself, and apply unit, that is R B equals 1. Here that is MA equals 1. MA is 1. Here RB is equal to 1. I am applying unit load because I have taken the direction downward only, because that is the reason I need not attach negative sign, all will be positive only. So there won't be any mistake occurring, chances of mistake occurring during your course of calculation. So this particular thing will displace like this. Now again, this is another case which you have to remember. Due to this, you will get displacement here, displacement here. This displacement is nothing but F12. That is displacement along coordinate 1 when unit load is given along 2. And this is nothing but F22 itself. Displacement along 2 when unit force is given along 2 itself. So this is the third case which you have to remember. I am giving here. So these 3 or 4 cases you can remember straight away before going for the exam. And there won't be any problem. If you have a load here P or W at a distance A from left hand, at a distance B from right hand, I am taking, of course here it is central load, I will give you a general loading case at A and B. If you put A equals B equals L by 2, then it reduces to concentrated load, and L is the span, A is the flexural rigidity, it will displace like that, and this rotation here, it is given by ML by, not ML, it is WAB by 6 EIL, 6 EIL into L plus A or L plus B. So this same thing, WAB by 6 EIL into L plus A. So here this side it is L plus A, this side it is L plus B. And displacement at any distance x, I will give it as I have given here, that you can remember straight away, that displacement delta at any distance x from left hand, it is given by W bx divided by 6 EIL into L square minus B square minus x square. This is the formula which you can remember for calculating the slopes and reflection due to eccentric concentrated load. These three standard cases you have to remember so that the problems can be easily solved. Using that, straight away I will do this. Now here W is 1, this is the applied load, so I will find out first F12. F12 is nothing but this, WAB by 6 EIL into L plus B. W is 1, A equals B is equal to 4 meters. WAB means it is 4 into 4 divided by 6 EI into L. L is 8 meters, EI is EI itself, 6 EIL into L plus B, that is 8 plus 4. If you simplify this, this is 12, 12 into 16. 192 divided by this is 48 EI, so this is nothing but 4 by 9. Naturally, F12 should be F21 because this has to be a symmetric matrix, I told, property of flexibility and stiffness matrices. And lastly, F22 you can generate. F22 is nothing but, that is the deflection here at this point. So x is equal to 4 meters, you can substitute. W is 1, B is 4 meters, x is also 4 meters, both are 4, divided by 6 into 8, 8 is L, 6 into 8 into EI, multiplied by L square, that is 64.
Minus
Square is 64 minus B square is 16 minus
X square
is 16. 16 no?
Yes sir.
16. X square is also 16. So here I think it is x square, okay, minus 3lx. That formula is also, we are getting more or less similarly. So this you will get
10.66.
How much?
10.66 divided by A.
10.67
67.
divided by
EL.
Yeah, fine. So I have generated the flexibility. That's all the exercise you have to make, and then you have to use force displacement relationship in order to find the redundant force. Then once you determine the redundant force, other reactions you can determine by simple equations of statics and then draw the bending moment and shear force diagram. So let us take the next step, or I will just show the flexibility matrix. Therefore, F is equal to, that is 2 by 2 matrix. It looks like this, 1 over EI, I will take it outside. So 1 over EI, F11 is 2.67, then F12, F21 is 4, then this is 10.67. So I will determine this F inverse also here. F inverse is equal to, this becomes EI divided by delta 2.67 into 10.67 minus 16. How much is that? 2.67 into 10.67 minus 16.
12.67.
12.67. That is your determinant of this into adjunct of cofactors. That is, this is 10.67. So this will be minus 4, 2.67. This 2 by 2 matrix you can easily invert in this fashion. That also I have inverted and kept. So then the next step, fourth step, to find redundance. That's the last step, to find the redundant forces. That is your MA and RB. What we have chosen as redundant, that I have to evaluate. So we have this D is equal to F into force P. This D is nothing but your dN1 minus or dJ or dr minus drL1, then dr2 minus drL2. I will explain what all these coefficients. So here dr1 is external displacement vector. It is given in the problem that we have to take along the coordinate 1. If they give some rotation along that 1 forcibly, externally, then you have to take it here. Similarly, dr2, if they say give support settlement, say support is settled by 4 mm or 120 by EI, that value.
Those are all joint loads.
Joint load, that's joint load. Is as in stiffness method, you have taken it as joint load. This is joint load and this is displacement due to given load. DRL1 due to given load, that's minus. There also PMF, minus PMF, you are taking. Here it is minus DRL1, DRL2 due to external load, that you have to take. And this of course F and is there. And this P is nothing but your redundance, MA and RB. The two redundants, that is the value I have to take. Therefore, here this is 0, no settlement of support is given. I could have included that. I will take that itself. Suppose if they give this P settles down by 120 by EI, that value you can substitute here straight away and you can solve that one here. This is the place where that change occurs. That support settlement or whatever it is given, that you have to substitute here. That is the only change, nothing other than that. And one day support settlement is given, then you have to choose the redundant as one of the force or as one of the redundants to in that direction. Suppose if they give support A settles, then you have to choose force at A as one of the redundant. That you have to keep it in mind. That's another thing. So the choice is with your hand. I told you, that one restraint is there or one constraint is there. If at all support settlements are given, then you have to choose that as one of the redundant.
Sir, if they give a couple value or joint,
then you have to choose. Suppose if they give this is rotated by certain amount, and of course that I have taken here MA, that's no problem at all. There instead of 0, whatever that rotation they have given in radians, that I will substitute straight away. That you have to.
So well before choosing the
While
redundant,
choosing
the loads joint or something.
before first step itself, while choosing the redundant, keep it in mind whether they have given any secondary effects, that is like support settlement or support rotation and all. At that time, at that point, yeah, wherever that particular thing is there, you choose that as one of the redundant force and proceed with your calculation, so that at this step you can straight away put that value and you need not have to bother about any other extra calculations, right? So next, here of course no settlement, no secondary effect, both are 0 here, 0 minus DRL1. DRL1 I have already calculated in the first step. DRL1 I have, where is it? How much is that? Remember? DRL1, DRL2. That you, here it is.
D.
1280.
1280.
Okay. That is 1 over DI. This is 1280. Here DR2 is also 0 minus 3200 equals. So now I will rub it off. So equals F, that let it be there as it is, F into MA or B. So therefore MA or B, MA or B is equal to F inverse into this. That F inverse I have determined here, that is EI by 12.67 into 10.67 minus 4 minus 4, 2.67, that is F inverse into this 1 over EI into
minus
this is
128.
minus 1280 minus 3200. So this EI get cancelled. You will have that redundant force value MA and RB. Because this is 2 by 2, this is 2 by 1, so this row and column are equal. Resulting matrix will be a 2 by 1. This is also 2 by 1. Straight away you can get the values of MA and RB. So this is 10.67 into minus 1280 plus 4 into 3200.
Minus 857.6.
Minus
857.6.
6. Similarly, this after dividing by
No.
that you divide by 12.67 also.
0.67, then minus 67.68.
Minus 67.68.
7.
This is 4 into 12.80 minus 2.67 into 3200 divided by 12.67.
Divided by 12.67.
That you can simplify, you will get that redundant forces. That redundant forces you can substitute here and calculate other reactions and then draw the bending moment diagram. That completes the problem.
So minus 270.
Minus
270.2.
that after dividing by
Yes.
minus 270.2.
0.24.
Okay, fine. So that completes your problem. Now you write your given problem straight away. That is this. This is your problem. So this is A, B, C subjected to full UDL of 60 kilonewton per meter. Now this RB, it is minus value you are getting. Earlier I have selected the coordinate as acting down. Now I will reverse that direction. So it has to be like this. So it is 270.2. This is my RB, which I have found out, and that the MA, that is 67.7. So earlier I took direction of the coordinate as clockwise. Now I have to reverse its sign. So the moment here it will be in this direction, that is 67.7. So now I will determine this reaction. You take moment of all these forces above J, you can find the reaction, this reaction RC. Then you equate sigma V equals 0, you will get RA. So like that, all other reactions you can determine, you can plot bending moment and shear force diagram. Since you got all support reactions. That's a very simple. This is last final exercise to draw bending moment and shear force diagram. This RC is nothing but this 270.2 into 4 plus this 67.7 and minus this UDL 60 into 8 into 4, this entire thing divided by total length 8.
96.43.
So this is 96.43. Then this RJ you can find out because total load, it is 60 into 8, that is 480 minus 270.2 minus 96.4, that will be your R8.
113.37.
113.3. So make sure this sum should be equal to total load. Naturally this is 3 plus 2, 5. Oh, I think this I will take it as 4.
Yes, sir.
Yes. The sum is 60 into 8, 480.
480.
480 you will get, naturally sigma V has to be 0, sigma M also has to be 0, sigma H is not at all coming to picture. So this is perfectly in equilibrium. Knowing all this, you can plot the bending moment diagram. That exercise, I will leave it to you. You can do it. Because the moment you know all the support reactions, because they are the only unknowns. Plotting bending moment diagram and shear force diagram, it is very easy. There is nothing you can take some section and find in that section Vx and Mx, plot it. One from left hand, another from right.
It's a general bending moment diagram.
Generally, you can full common bending
Moment
diagram.
and V moment.
You need not superpose. Otherwise, if you want to superpose, you take this and this as the unknown. Then straight away you could have plotted bending moment diagram at least. Had you selected MA and MB as the unknown. Why I selected this RB means to explain that support settlement thing also, because now I will give that problem support settlement. For this problem itself I will include this second problem. You can take it as if support B settles down by 120 by VI. Find the change in results. So I told you already, the change occurs only at this position. The other things are all same. Only thing is, by selecting the redundant, you have to select this RB as one of the redundant. That you have to make sure, because support settlement occurs at that point. You have to choose wherever that secondary effect is there as one of the redundant, so that you can just do the calculation without any problem.
Sir, and also when we are drawing bending moment diagram, let's say a couple of 67.7. So we have to show that separately for that value.
That also can do.
Because that's a.
So I will show you that. Suppose Mx you take it here. You take a section x at a distance x to draw bending moment diagram. Mx is equal to 113.4 x due to this. I will take free-body diagram towards that. Then this is minus 67.7 and this UDL, that is minus 60 into x into x by 2, that is 30 x squared. Naturally it is a parabolic because it is second degree. You can put x is equal to 0. Right?
We are getting minus
0, it becomes minus 67.7. So that means here this becomes 67.7 at that point. Then you can find out what's the bending moment here. So that is whatever bending moment can be, you get that straight away you get. So you can plot it by parables. Second degree curve.
minus 94.1.
Whatever, if it comes at this point and 4.4, this is the diagram. You need not superimpose that free movement diagram because already I have taken that here. So you will get the net bending moment diagram straight away. So probably you may get bending moment diagram like that fashion. Kind of fully. So all are, this is negative we get, and here maybe somewhere, I don't know, probably it may go like that. It may go like that. Bending moment diagram. So this is negative at some point here. It may get 0. You have to get some positive movement at some point, then automatically it will be 0. You may get bending moment diagram in this fashion. This is negative, this is positive, negative, positive. Here of course it has to be 0. Here it has to be negative because it is intermediate point and in between intermediate support, and in between there should be a positive quantity. So that you can check out. On same lines, shear force diagram also. You remember the shape of the bending moment diagram has to be like this, the net shape. Because when you are even in stiffness method, you have seen after plotting the fixed moment diagram, superpose that, you will get some portion positive, negative, positive like that. It is in the same fashion you will get that you can just complete.
Thank you.